Alright guys, here we go. This is our pretty much our last explanation for our systems of linear equations. Um, Alright, it's going to be more of a advanced type proof. So I'm just going to outline the methods of elimination more closely. So we go to methods of elimination. There's basically three steps that we have to deal with. Our first step is we interchange any 2, 3, 4, 5, 6, any arbitrary value of equation. So we'll just call it the I and jth equation. Then we multiply them by any non-zero constant. So multiply by any non-zero constant. And then we replace the ith equation by c, which is any constant value, times the jth equation. Plus the ith equation. And in this case, I is not equal j. So then what we get in short form is we'll get a I x1 plus a I 2 x2 plus a I 3 x3, and this will go on for any a I and xn value where n is just the sequence of continuation. And we'll just set that equal to any bi value. We'll just say, so let's go by CA J1 plus AI1, which is when we're multiplying the jth equation by the ith equation for the a value by any constant, adding it to there, hopefully to cancel it out or eliminate one variable. What we'll get J2 plus AI2, sorry, and that'll just continue in the same sort of way where we get CA JN plus AIN XN, and that'll just give us CBJ down from there plus BI. And let's circle that so you can better see that. That goes down here. So not so simple anymore when we break it down, but again, if you wanted a proof of it, those are just our basic ways of solving it. Now, let's take a more complex approach to this. So I'm going to give you sort of like an advanced problem. Let's say, suppose we take the ith equation of a linear system, which I'm going to write down below, linear system below, and multiply it by a non-zero constant c. Constant c, which, or just assume we have this linear system, where we have a11 this is the, well, later in the matrix you'll know that that's the row and that's the column. But it doesn't really matter right now. Well, we have ax1 plus a12, where we change the column, x2 plus, and this will go for any arbitrary value, a1n, xn equals b1. b2 is the same thing, except we now change it to 1 plus a22, x1, x2, plus a2, and xn equals b2. And then we just take this down, or we multiply it by any sort of constant value. Go down here. And I'll zoom out so we can see this better. Oops, sorry. Zoom out so we can see this better. And that'll give us a AI1. Zoom in, actually. So we can write a little bit smaller, and then I'll zoom out. Sorry about that. I'm going to write these down in different colors so you can see it better. We get CAI. Suppose we have the CAI x1. And these are just, you know, placeholders for the values that we can deal with on any sort of regular basis. Plus CAI and xn equals CBI. And then you do the same thing. And I'll just go down to CM1. We'll just call it M1 for matrix 1. x1 plus AN2, x2 plus AMN, row and column, xn equals BM. Now, if we have, in this particular example, if x1 equals s1 and x2 equals s2, and it goes on for any xn value equal to sn, the solution is going to be the same, except the possibility for the ith equation. For the ith equation, you would just take the constant out, and then you just get AI1 S1 plus AI2 S2 plus any arbitrary AIN value Sn equals CBI. And then you get the same thing if you just distribute them all through. You'll just get CAI1 Sn plus C. The AI2 S2 plus the arbitrary value for CAIN Sn. And this is CBI for that value. So the ith equation is pretty much satisfied in all these cases. Now, what does this look like graphically? And for this, I will zoom out. What does this look like graphically on our board? Well, if we're dealing with something with, let's say, a 2x2 matrix, let's draw this. Just saw 3 graphs here. Sorry about the graphs. And I'll make this a little bigger. Say we got one line there, and one line there. Right over here, this just shows us we're going to have one solution. When we have the graphs where they're parallel or they'll never touch, this is only no solution. And when the lines lie on the, when it's the same line, it's infinite. Any solutions. So that's just sort of, and it goes the same for planes. If you have 2 planes or 3 planes and they intersect at one point, one solution, and so on and so forth. So that's always the same for planes. as well. Now, sorry about that. This is basically it for any sort of value. Over here, I'm just saying that any constant value, if you multiply it by, it doesn't really matter what constant you multiply it by, because you're going to get the same solution for any given value. Just whatever it takes to eliminate the variables. That's all. And next we'll be covering matrix. We'll be getting into matrices, and this will all start to make a little bit